One of the goals of science is not only to uh, make formulas for or make experiments, but also to reduce down complex problems into simpler ones. And one such problem that's of immense interest is can be explained by the following reaction. So you have something that's called as ethyl acetate, and the formula for ethyl acetate is CH3 CH3 COO C2H5. And in ethyl acetate, you add water, and once you add water and you add some acid for catalysis, you get acetic acid, you get ethanoic acid or acetic acid, whatever you want to call it, and you get ethanol, and you get ethanol. The kinetics of this reaction is really interesting. So initially you start with some concentration of this ethyl acetate, and it's a relatively small concentration. And to it you add a huge amount of water. Water is in excess, and initially there is 0 moles of both of the products. And let's say after some time, after some t equals x seconds, all of the ethyl acetate has been converted into the product. So here you are left with 0 moles, 0 moles. And here in H2O, you have used up, if you have used up 0.01 moles here, you are going to use up 0.01 moles here as well. And if you use 0.01 moles here, you are going to make 0.01 moles of these two products. And if you note this number, the amount of water that still remains is 9.99. And if you want to write the rate for this the rate expression, the rate equation for this equation, for this reaction, you are gonna write rate equals some constant k, the rate constant, times the concentration of ethyl acetate times the concentration of water, and that makes sense. However, if you look carefully, if you look at the percentage change in the concentration of ethyl acetate, that's close to 100%. However, the percentage change in the concentration of H2O is negligibly small. It's almost 0%. So what you can do is, since there are no changes in the concentration of H2O, negligibly small change, you can assume this to be a constant. So assume this concentration of H2O to be a constant. Assume to be constant. And it's not only true for this reaction. In any reaction where you have an excess of solvent and in which you perform a certain reaction, the solvent still remains in appreciably equal concentration to what initially it had began from. So in this case, what you can do is you can write all the constant terms together. So this term, the concentration of CH3COO C2H5 ethyl acetate, that is a variable that does changes significantly. However, these two terms, K and the concentration of H2O, they are both constants. So you can club them together. So another way to write the rate will be K times the concentration of H2O times the concentration of ethyl acetate. And by doing this, you essentially get a new constant. Let's name that constant as K dash. And notice now you can write the rate as K dash times CH3COO C2H5. And notice what we have done here. We started with a chemical equation that had that had order of 2, so 1 power here and 1 power here. So this rate equation had an order of 2, and you achieved an order of 1 by setting the concentration of the solvent to be a constant. And in this case, in the final, you have a first order reaction. So in reactions like this that are not first order but seem to behave like first order approximately, these are called pseudo first order reactions. And the same argument would hold true for any order. The word pseudo just means that it seems to be something, but it's really not. So it's a really great approximation when it comes to things happening within the solvent. And some other example of that would be the inversion of cane sugar. So cane sugar is a natural product. Its chemical formula is C12H22O11, and when it reacts with water as a solvent and in water with some acid catalyst, it decomposes into glucose C6H12O6 and fructose. Both of them have the similar formula. However, they are a bit different. That's part of organic chemistry. However, for now, assume this is a first order reaction, and it's a special type of first order reaction. It's a pseudo first order reaction. Pseudo first order reaction. Let's try solving the problem on this. So let's start by taking I have some numbers with me, so let's try the hydrolysis, that means reacting with water, of methyl acetate. Now methyl acetate is just CH3COOCH3, and you're adding water to it to form something, and you really don't care about what the products are. And what you do is you figure out the concentration of this substance, this ester. This is called an ester, by the way. You figure out the concentration of ester at different times. So the chart that I have with me right now, it represents time in minutes and concentration in moles per liter inverse, so molars. So at beginning, the initial concentration is 0.8500. After 30 minutes, you have 0.8004, and at t equals 60 minutes, that is an hour. The concentration is 0.7538, and at t equals 90 minutes, you have 0.7096 molars. And what you can do is you can try a few things. What you can do is start by taking into consideration whether this can be a pseudo first order reaction, and that should be some of your intent, because whenever you see a solvent, insanely concentrated solvent, water is one of them, you think about pseudo first order reactions first, and let's proceed through that route. Now what you can do is you can write, let's say that this was a pseudo first order reaction. Then you could have written the rate of this reaction as K times H2O times CH3COOCH3 again, and this thing we say this is some other constant K dash. And notice we also have one more stuff. We have learned about first order reactions, that for a first order reaction you have, if the rate constant is K, and in this case the rate constant is K dash, so let's take that, times multiplied by the time equals natural log of C naught the initial concentration. So let's use the standard de facto that we're using. So initial concentration over the concentration at time t. And that is one way of representing this. And we had also talked about that you can write the natural log as 2.303 log of a naught over a. And both of these are equivalent ways of writing what you have. And what you could have done, you could have basically sort of tried finding out the k. You could have tried finding out the k. So k dash, we'll first try finding with k dash, since for a second order reaction with two reactants, the math becomes increasingly difficult. So let's try with the pseudo first order thing. So k dash is equal to 1 over t of 2.303 times log to the base 10 of a naught over a. And if you try just what you will do now is you will take this chart right here and you would start putting out the values of k dash in here. So for example, at t equals 0, you can't figure out anything, so let's just leave that for now. At t equals 30, let's do the math here. The k dash is equal to 1 over 30 times natural log of a naught here is 0.8500 over 0.8004. And if you do that, if you use a calculator or something, if you do something, if there is log 10, there will be a 2.303 as well. And you could use a calculator or something, and you would be given log tables, by the way, if you are intended to solve this problem. You would get the k dash to be equal to 2.004 into 10 to the power negative 3. And the units in this case, since it's a first order reaction, it assumes the units will be minutes inverse, since we are taking time to be in minutes. And what you could do is you could do that for t equals 60 minutes, and you could do that for t equals 90 minutes. So for t equals 60 minutes, if you do the math again, you would arrive at 2.002 into 10 to the power negative 3. And in last, for t equals 90 minutes, you would have 2.005 into 10 to the power negative 3. So if you see carefully, the k dash is increasingly constant. It's sort of just fluctuating near a certain value. So you can take the k dash to be approximately equal to 2.004 into 10 to the power negative 3 minutes inverse. And from this you can try finding out the original k, not the k dash, the original k from this. So you could now use the relation that k dash equals k times the concentration of H2O, and k dash in fact is 2.004 into 10 to the power negative 3 minutes inverse. That is equal to k times the concentration of H2O, and this is an interesting problem. It's equal to 55.55 moles per liter. And how did I derive this? Well, you could try that by using the formula for molarity. In that, what you would do is the number of moles of H2O in 1 liter is equal to 1000 over 18. Why? Because 1 liter contains 1000 grams of water. It contains 1 kilogram of water, and 1 kilogram has 1000 grams of water, and 1 mole contains 18 grams. So number of moles of H2O in 1 liter is 1000 over 18, and you divide that entire expression by 1 liter to get their molarity, and that would be equal to 55.55. So here you have the k dash equals kH2 equation to be equal to it will be equal to k times 55.55 moles per liter. And if you take this to the other side, that means that you're dividing then. You would arrive at K to be equal to 3.64 times 10 to the power negative 5 moles inverse liters minutes inverse. Hopefully that introduces pseudo first order reactions for you. In general, what you could do is you could take any pseudo order reaction with respect to any order, anything, and you would still have a correct situation as long as one of the reactant has a astoundingly large concentration, and it doesn't make sense to change it in every reaction. See you in the next video.